In this video, I will explain about the application of node voltage method for network solution for AC networks by taking an example. So the circuit is simple, which was also used in the last lecture to apply for the mesh analysis or loop analysis. So there is an inductor, resistors, two resistors, and there is an inductor, and the current is 100, or the voltage is 100 voltage, and I am finding out one node here. So the step one is identifying the nodes. So in this step I have identified one node here, and the second node is a ground node. So this is a simple step, simple example to demonstrate the solution in AC networks. So if I am applying, if I have the branch currents as I1 and I2 and as I3, then what I will get is I will get I1 is equal to V minus 100 divided by 10, which is equal to V minus 100 of 10, since this is cos theta minus sin theta and theta is 0, and my I2 is equal to V divided by 10, and my I3 is equal to V divided by J of 10. So these are my first step set of equations which I get. So I can find my V by, the first step is identifying or writing all branch currents in terms of node voltage. So my I1 is equal to I2 plus I3. This is my equation, by applying the KCL, whatever I will get. So and when I am substituting each of the branch currents, whatever I will get is V minus 100 divided by 10 equal to V by 10 plus V divided by J of 10, which is equal to V by 10 minus of 10 is equal to V by 10 plus V divided by J of 10. So this and this will cancel, and my minus 10 is equal to V divided by J10, which gives my V equal to minus 100 of J. Again there is a check which is correct. I1, what was my I1, I2 and I3. So if I say this is my second equation, this was my second equation and this was my third equation, whatever I have got, then if I am substituting the value of the V back in the voltage, so the second step is to get the node voltages. So I have only one unknown node voltage in this case, which was V, so I found that, and my I1, which is equal to minus 100 J minus 100 divided by 10, which is equal to minus 10 J minus 10, which is equal to minus of 10 J plus 10. And my I2 is equal to minus 10J by substituting the value here, and my I3 is equal to minus 100J divided by 10J, which is equal to minus 100 of J into minus J divided by 10 of J into, or 10 of just J into J. So dividing and multiplying both by J, what I will get is, I will get here minus 100 into minus 1 and here 10 into minus 1. So this will be my minus 10. So my I3 is equal to minus 10 in this case. So just to check if I have got it correct or not, then my minus 10J minus 10, which is substituting in this equation, is my I1, which is equal to minus 10J, which is equal to my I2, and my I3 is equal to minus 10. So whatever value I have got is correct and it can be validated by this same thing. The other way to solve this, if you are having more than one node, it is also possible to apply the Cramer's method to solve this. But just to demonstrate, I have taken a simple example, and it's possible to solve circuits having multiple components. Usually it's when you have more, the network becomes larger and it involves components involving the AC, like AC power source, voltage source, or a resistor or inductor. The solution will become very large because due to the multiple equations. So you will have to take care, and usually in exams also it might be possible that you might get questions related to the AC circuits which are large, but usually the questions are small, involving smaller networks when the AC components or AC circuits are used. One of the reason is that if you are going to solve for AC networks using the mathematical solutions, then for solving the AC networks the equations becomes larger and the solution is time consuming.